Okay, so it is a pleasure to have Florian Frick today, and he will tell us about chirality and quantifying embeddability.
All right, yeah, thank you. I'd like to thank the organizers for putting together this workshop. I think it's a great idea, very useful idea. Somehow, I feel like I'm somewhere between applied and quantitative topology myself, so maybe my mathematical house gets road access to this, so that'd be nice. Yeah, please do interrupt me with questions, type into chat. I hope I can monitor chat throughout. Feel free to turn your camera on. I can see you on my screen. You can, give me a thumbs up or thumbs down. Okay, so this is joint work with Mike Harrison, who is currently a postdoc at the IAS. And what is the goal? The goal is you're given a space that is triangulable, can cut it into simplices in a nice way. And we want to find bounds for the topology of the space of embeddings. So an embedding, and if X is compact, we can just think of an injective continuous map into RD. And we want to understand this space of embeddings, and we want to do it in terms of the combinatorics of X. So there are many possible ways, many possible strategies, but we want to do this via the combinatorics of the space X. Okay, so notice this could potentially be interesting because X does not embed into RD. Well, that's a very classical type of statement, a non-embeddability result. And X does not embed into RD. Well, that just means the space of embeddings is empty. And I think it's a somewhat natural question to ask is, in this situation that X does not embed into RD, is it perhaps possible that if it does embed into RD plus 1 or RD plus some constant, that you can, in a quantifiable way, constrain the embeddings? The space of embeddings is not very rich if you just go up by one dimension. Can you make sense of this? Before I do this, seeing how this is supposed to bridge applied and quantitative topology, let me give you a motivation that's actually applied, which is chemical topology. So in 1912, so more than 100 years ago, the chemistry Nobel laureate Willstätter raised the following question. Consider a molecule. So a molecule, this looks like this. Like these are, here carbon atoms, and there are chemical bonds between them. And for the purposes of this talk, you can think of these chemical bonds as actual rods, which is of course wrong, but let's pretend they are. Consider a molecule that forms a ring. So a ring of atoms joined by these chemical bonds. Do the properties of a substance depend on whether the molecular rings are pairwise unlinked or pairwise mechanically linked? So not chemically linked, but actual molecules that you have a ring, you have another ring, you link them. Do the properties of the substance depend on whether molecules are linked or not, so that one molecule drags along the other? Yeah, that was an interesting question in 1912, but really people didn't have any good way of answering it. And it took until the 1960s, early 1960s, until Wasserman wrote a very interesting Scientific American article about isolating catenane. So catenane meaning molecules are linked, right? And how do you do it? Well, in the way that many of us do mathematics, he used a probabilistic approach. So he had a bunch of molecules that were just long chains, and he made them bite their own tail, and he just hoped for many of them to link. And this actually works, and you can isolate the linked ones, and then you can look at the substance. Okay. And somehow the outcome of this is the topology of a molecule does in fact determine the properties of a substance. So if you have a flexible molecule, depending on how it sits in space, whether it's linked with other molecules, whether it's somehow twisted, influences the properties of a substance. For example, one type could be an oil and another could be a solid, depending on the actual topology of the molecule. In the 1980s, Walber et al., they actually built molecular Mobius strips. So tiny 6-atom molecules Here's a schematic picture of this. So this molecule, sorry, this atom over here is the same as this, and this is glued to this, and then that's a Mobius strip. And why would you do this? Well, on the one hand, maybe it's interesting to synthesize this. On the other hand, the boundary of a Mobius strip is self-linked, right? It's somehow twisted in itself, so you can actually get linked things this way. Now, Mobius strip has a left-handed and a right-handed version, depending on whether you twist this way or that way. These two Mobius strips are different, right? That's what people call a chiral. It's chiral. It has a left-handed and a right-handed version. Somewhat interestingly, it's not actually a Mobius strip. It's what I said here. It's K33. It's a complete bipartite graph on 3 and 3 vertices, because there's no way to, fill in these plates.
But this right and left-handed is only for embedding in R3, right? Because in R4
absolutely.
they are the same.
Yes, but yeah, we do chemistry in R3. But yeah, that's a good comment. That of course this depends on which dimension we're in. For the Mobius strip in R3 and in R4, the two are the same, right? But yeah, you can't fill in these plates. So it's actually K33. So you might ask, is K33 in R3? Is that actually a chiral embedding? Is every embedding of K33 left-handed or right-handed? So this becomes an actual question of topology, I would say, and it was answered by a mathematician in the journal Topology in 1986. Yes, K33 is indeed chiral. And this somehow was a starting point to mathematicians really investigating this property for embeddings. Okay, so let me define precisely what I mean by chiral. So an embedding of a space X into RD is chiral. There is no ambient isotopy from F to its mirror image. Okay, let me unravel these words. First, mirror image, that's easy enough. A mirror image is just the reflection of what you have in a hyperplane. Right? So you have your embedding, you choose your favorite hyperplane, you reflect in that hyperplane, what you get is the mirror image. Doesn't matter which hyperplane you reflect in, they're all the same up to ambient isotopy. And ambient isotopy means you have this map, this continuous map from RD to RD. Well, it has a time parameter. At time 0, it's the identity. At time 1, you've deformed F into its mirror image. And at every step in between, you're homeomorphism. Right? So imagine you take your embedded space and your space X, and now you have to deform the entire surrounding ambient space in such a way that at time 1, you have the mirror image. Okay. Let me pause and see if people have questions about the definition or comments about it. I want to make one point that I think is important here already, which is we're not taking symmetries of X into account. Yeah, so it's a labeled thing. The point f of x has to go to the point reflection of the point f of x in the hyperplane. Yeah? It's not the same as just taking the set f of the full set x and trying to deform it into a reflection hyperplane. That's also a valid notion of chirality that you can investigate. That's not what I mean for the purpose of my talk for simplicity. I really want f of little x to go to the reflection in x. There's a question whether this is related to orientability. Let me see if I can say, I mean, my first answer is not in some obvious way. I mean, it's certainly, I don't see any obvious relation between the two. Yeah, so you can take, yeah, I don't see any obvious relation. Okay, so this is titled From Non-Embeddability to Chirality. That's what I want to do, because observe the following. If x is embedded into Rd, then you can think of R to the d as a hyperplane in Rd plus 1, right? And then, well, it's its own mirror image, because take this hyperplane to reflect in it, nothing happens, right? Everything is fixed. And So if you embed X into RD, then this gives you an embedding that is not chiral because it's contained in a hyperplane, okay, into RD plus 1. So you can ask the question, given any non-embeddability result, X does not embed into RD, can you prove the stronger chirality result in RD plus 1? Right? Because if it's chiral in RD plus 1, it cannot embed into RD. That's the type of question I want to ask. Is that an acceptable question to ask for now?
Florian, there's one question from Chen.
There's a comment that any O of D symmetry, any orthogonal symmetry can be realized as a special orthogonal symmetry of the embedding.
No, it was my attempt to answer the previous question.
Do you want to say a few more words about it?
No, that's it.
Okay. Yeah, so what I want to do is I want to come up with a very general non-embeddability result and then convince you that it actually extends to a chirality result. And I want to do this in terms of the combinatorics of triangulations of X. So let me try to explain a very general non-embeddability result in terms of the combinatorics of X that I then can try to extend. And so I'm taking a triangulation of a space, a simplicial complex, so a bunch of simplices glued together such that every face of the resulting complex is uniquely determined by its set of vertices. That's what I mean by a simplicial complex. And then I have this parameter here. That'll be the combinatorial parameter that we're interested in. So if I had to read it, I would say it's chi of the Kneser graph of the non-faces sigma. But it's just one number. And let me explain this number to you. It's the least number of colors needed to color the non-faces of the simplicial complex. So all the subsets of the vertex set that aren't faces of your simplicial complex, such that disjoint non-faces receive distinct colors. Okay. Maybe easier to think about an example. So here's a simplicial complex, the complete graph on 5 vertices. So 5 vertices and all 10 edges. So what are the non-faces? The non-faces are all subsets of 1 through 5 that have at least 3 elements. All of these are not faces. But color them all red, right? Every single non-face is red. Now, any 2 non-faces, of course, overlap because they both have at least 3 elements and they're from a 5-element set. So no 2 non-faces are disjoint. No 2 non-faces of the same color are disjoint. So that's a valid coloring. Chromatic number is 1 in this instance. All right. And then the very general non-embeddability result that I want to state is due to Zakaria. And I put here 1990s because it's something he's developed over a bunch of papers, and he's never actually stated this result, but essentially that's the result he could have stated and the result he has proven, which is if you have a simplicial complex on vertex set 1 through n, then just take this parameter of this coloring parameter that we just defined and look at the number n minus 2 minus this number of colors. Then your simplicial complex does not embed into RD. Right? This is this D, this number, it doesn't embed into it. Okay, that's a relatively general non-embeddability result. Let me see. So for example, K5, we just saw K5. Chi of Kg of K5 was 1, we just agreed, and n is 5, and 5 minus 2 minus 1 is 2, so the complete graph on 5 vertices does not embed into the plane. That's good, that's what we want. In a similar way, you can look at all the k-dimensional faces in the 2k plus 2 simplex, the k skeleton of the 2k plus 2 simplex, because non-faces, right, up to k plus 1 vertices, everything is a face. And then non-faces have k plus 2 vertices, and for the same reason as before, any 2 non-faces overlap. So the chromatic number is again 1, and that means that the k skeleton of the 2k plus 2 simplex does not embed into R2k. Right, and that's usually, that's what people sometimes refer to as the Van Kamp and Flores theorem, which I've tried to investigate this. Apart from graph non-planarity, this seems to be the earliest non-embeddability result. Now, so, okay, maybe if you say Borsuk-Ulam says, you know, the two-sphere doesn't embed into the plane, then that's a few years earlier. But that's really it then. Similarly, K33, the complete bipartite graph on 3 and 3 vertices is not planar. Okay, what are the non-faces? I guess I can be fancy and do such a thing. The non-faces are, you know, here are the minimal non-faces, and it's enough to care about the minimal non-faces. 3 edges on the right and 3 edges on the left are the minimal non-faces. And now you declare these to be red, and you declare these to be blue, and then, you know, we have it. Non-faces of the same color are not disjoint, right? So this is 2, and 6 vertices minus 2 is 2, so K33 is non-planar. Okay. Well, one last example, just to really convince you that this is a general non-embeddability result, and you can get all kinds of results as a corollary. So here's my favorite triangulation of the real projective plane, which is a half icosahedron, the quotient of the icosahedron, right? So here's the top of the icosahedron, and then here on the boundary, you see we have identifications. This vertex is that vertex, this vertex is that vertex, and so on. So it really is a triangulation of RP2. It has 6 vertices. And for any non-face, minimal, so all edges are present, right? Every single edge is present. Non-faces have at least 3 elements. If you pick any non-face, for example, 1, 2, 3 is a non-face, right? It's a path that goes this way, but it doesn't span a triangle. If you take the complement of it, it will be a face, right? So 1, 2, 3, the complement is 4, 5, 6, and indeed 4, 5, 6 is a triangle of my triangulation. Now, so this is a complementary triangulation. For every triangle that's in it, the complement is not, and vice versa. But that's just a different way of saying the chromatic number is 1. All the non-faces intersect, which means 6 minus 2 minus 1 is 3. RP2 doesn't embed into R3. Okay. Well, you know what's coming. I mean, here is Zacharias' general non-embeddability result. And here's a consequence of what Mike and I proved. The same thing, but now a chirality result. And so if sigma is a simplicial complex on 1 through n, same parameter, n minus 2 minus chi, then any embedding into now RD plus 1 is chiral. Now, there's a left-handed and a right-handed version, which is more general than saying it doesn't embed into RD. Yeah, there's a question, why do I keep writing KG here? What does this even mean? By KG is short for Kneser graph, right? So what this is telling you is for this simplicial complex, now build a graph. The vertices are all the non-faces. Every non-face is a vertex of a graph now. And 2 non-faces are joined by an edge if they're disjoint. And then this is really the chromatic number from graph theory of this graph that you constructed. The graph of non-faces where disjoint edges are joined. Disjoint faces are joined by edges. Okay. Good. Well, corollary, okay. Everything we just said, you know, now you have the chirality result, right? K33 and R3 is chiral. Well, Simon already knew this. RP2 and R4 is chiral. This is a fact people know, but I can't point you to the literature. If you know where to find, you know, an early reference that RP2 and R4 is chiral, please let me know. CP2 and R7 is chiral. This is known because Arkady Skopenkov completely classified embeddings of CP2 into R7 up to ambient isotopy. You get a chiral version of the Van Kampen-Flores theorem. This seems to be new. And yeah, these things you get as corollaries.
Sorry, and for CP2, do you have to take the CP2 the 9 vertex?
I'm not sure that you have to take it, but that certainly works because there's a 9 vertex, right? That's a good comment, thank you. There's a 9 vertex triangulation of CP2 that has the same complementary property as the triangulation of RP2. And then for the same reason, you get this chirality result. There is a 16 vertex triangulation with this complementary property that we think triangulates the quaternionic projective plane, but I don't think anyone has proved that. So you get the same chirality result for the space that is triangulated by that, presumably the quaternionic projective plane.
It actually is proved.
It is proved.
Yeah, it's proved quite recently, like it may be in 17 or 16 by Denis Gorodkov.
Oh, that's fantastic. Can you put the name in chat, actually? That'd be really helpful.
Oh, sure.
Thank you. That's good news. Yeah. Well, I want to come back to this point that I emphasized in the beginning, that our notion of chirality really requires that every point f of x goes to h of f of x. It's like it's labeled, right? All the points have little labels, and these labels. Thank you for the name. The labels have to go to the correct mirror image. Of course, you could just say, I want this at a set level, right? The entire set, my embedding of x goes to the mirror image. This really is a different notion. So as an example, here's a result from the 90s, where, so what's proven, complete graphs, it's completely classified which complete graphs are chiral in R3, right? And it's the complete graph on 4n plus 3 vertices is chiral in this weaker sense, and all other complete graphs are not. Whereas what we get, all complete graphs, K5 and up, are chiral in the strong label, in the strong labeled sense. So if you are more interested in the weak sense, what you should do is first prove chirality in the sense that I'm discussing, and then incorporate symmetries. That's usually how these proofs go, right? That's how it was proved that K33, for example, is chiral in the stronger sense. And for some spaces, there's no difference. For example, for RP2, any automorphism of RP2 is the identity up to isotopy. So there's no difference whether you incorporate these symmetries or not. I want to give you at least an idea of what goes into a proof of such a result. And for free, without thinking much, we get notions of what I call higher achirality. So notice if you have an isotopy, not even an ambient one, just an isotopy through embeddings of an embedding F to its mirror image. So a homotopy, and at every point you're an embedding. Then what can you do? You start an F and you go to its mirror image, and then you just copy what you did, but now you take all the mirror images on this upper semicircle. Right? So lower semicircle is your homotopy, your isotopy to the mirror image, and then copy mirror images on the upper semicircle. And that constructs a map from the circle into the space of embeddings that has this property that if you go from one point on your circle to its antipode, you flip from the embedding to its mirror image. So it's a map that preserves a Z-mod 2 symmetry. It's an equivariant map. And I think it's very natural to ask, once you have exposed this embedding as not being chiral by having this circle in your space of embeddings, can you fill this circle with a disk? Is it a homotopically trivial way of deforming your space into its mirror image? Is the deformation of your space into its mirror image homotopically trivial? And that's just the question, find the largest sphere that maps into the space of embeddings. That's what people call the co-index of the space of embeddings. So that's what we can compute in this way. Yeah, so what are some elements of a proof? What goes into it? Well, for your space X, consider the ordered configuration space of 2 points in X. So any 2 points that are not the same, if you like, you can think of this as a space of embeddings of the space 1, 2 into X. That's the same thing, right? X embeds into D space, that induces a map, a Z-mod 2 equivariant map from the 2-point configuration space to the D-1 sphere, just by saying, take 2 points, evaluate them under your embedding and subtract. and now, you know, normalized to be in the sphere. And now this is an equivariant map into the sphere. Okay. And in the same way, if you have a non-chiral embedding, so you have this Z mod 2 equivariant circle in your space of embeddings, well, that just means there is a Z mod 2 squared map from S1 times the 2-point configuration space into SD minus 1. And now you see why it's all the same, whether you ask this question for S1 or SK, because for SK, you just have, you know, a map where you write K instead of 1 here. Right. Tiny technical difficulty is we want to work with the deleted join instead of the deleted product. You know, so instead of points, we have abstract convex combinations of distinct points. You know, so that the configuration space sits in here inside of this space if you insist that lambda is 1/2. Right? But lambda can be anything between 0 and 1. And then what you do is you just, if someone gives you a Z mod 2 equivariant sphere in the space of embeddings, you just either curry or uncurry, I'm not sure what it's called, this map to say, aha, this is a map from SK times the space I'm mapping from, just defined in this way. Right? Just by plugging into this map. And well, if you have this, and at every point Z, this is an embedding, well, then you can write down this map, right? That takes any point in the deleted join. Here in the first coordinate, you measure whether lambda is 1/2. This is only 0 if lambda is 1/2. And here, well, if lambda is 1/2, then forget about lambda and 1 minus lambda. You measure whether fz of x is the same as fz of y, right? So this map that I just defined, if fz is an embedding at every point z, then this map doesn't have a 0, right? Because this is never equal to that. And if it is, then this is not 1/2. So that this is not 0. And this map respects symmetries, right? Just imagine if you flip lambda x and 1 minus lambda y, then you flip these two entries and these two entries, so you flip to the negative. If you flip from z to negative z, then this flips to its mirror image, right? So this map has a bunch of symmetries, and now we can obstruct the existence of equivariant maps in the usual ways. And the way that combinatorics enters into this is that this coloring of non-faces, you can just use this to, by hand, construct a Z mod 2 map from this the n-1 simplex and its deleted join. So if this means anything to you, this is a cross polytope. Right? It's a Z mod 2 equivariant cross polytope. Think of an octahedron. Right? This is an octahedron that your triangulation sigma lives in. And you use the C colors to construct a map to RC in the stupid way where you map non-faces, you know, red is the first unit vector and blue is the second unit vector and so on. And you just write down this map. And this map will have the property that the zeros are exactly the configuration space of sigma. And then, you know, you just put it all together and now you have a map from SK times Sn-1, 2 spheres. And this is a Z mod 2 equivariant map into Euclidean space, and you want it to have a 0. And now you just need to decide whether such a map exists or not. Okay, I think that's all I'm going to say about the proof, unless people have major complaints or minor complaints.
I don't have a complaint, but just maybe a question. So do we know what happens to this chi j after subdivision? Does it stay the same?
Yeah, that's a good question. No, it doesn't necessarily. So we really, you know, in the space of triangulations, you really want to optimize. And I'm not sure that I have even a good heuristic for how to optimize. It seems that smaller triangulations are better.
I see, thanks.
But yeah, that's again, yeah, that's a question I wish I knew an answer to. Right. So in some sense, what might be interesting here is instead of the space of embeddings where we put this ZMod2, this involution that maps a space to its mirror image. Let's get a little more outrageous. I'll put a little minus in the index here. And by that, I mean, it's still the space of embeddings, embeddings of X into RD with a compact open topology. But now my new involution is F maps to, and I reflect in the origin, negative F. Okay, so I want to investigate when an embedding can be deformed into everything goes, all the coordinates go to negative instead of just one. And on the one hand, I mean, one reason why this might be interesting is because we can prove exact bounds. I'll give you a better reason in a second. But, here we have exact bounds, for example, for RP2 in RD, the coindex, the largest sphere that equivariantly sits in this space, has exactly this dimension. If you plug in d equals 3, 3 divided by 4 rounded down is 0, minus 1 is negative 1, the space is empty. There are no embeddings. Right? There are no embeddings of RP2 into R3. If you plug in 4, 4 divided by 4 is 1, times 4 minus 1, so in total 3. There is an equivariant 3 sphere sitting inside the embeddings of RP2 into R4. That shouldn't surprise you, because fix your favorite embedding and send it around by, just symmetries of R4, which you might think of as quaternions, and unit quaternions, give you all kinds of embeddings. And similarly for CP2, we can prove exact bounds in all dimensions.
I'm sorry, can I ask you something? I'm getting confused here. So what is coindex on this slide?
So sorry, coindex. So this means, so if this is K, then this means there's an SK map that's ZMod2 equivariant into the space of embeddings. Yeah, so this higher notion of achirality.
And embedding minus just have a different Z2 action.
Right, it has this ZMod2 action.
But but depending on the parity of D, it's the same as the reflection or just identity up to isotopy.
That's right. Yeah, so it is chirality only in odd dimensions. It is a higher dimensional version of chirality in odd dimensions.
Okay, thank you.
Right, so RP2 we already proved is chiral in R4. That's not in contradiction with this coindex being 3. Right, for the reflection in the hyperplane, it's 0, but for going to the point reflection, this is 3. Now, why might this be interesting? The less silly reason. There's this notion of non-singular bilinear maps. So you have a bilinear map from RP times RQ to RD. And it's called non-singular if it doesn't evaluate to 0 unless you plug in 0 for one of the two entries. So if X and Y are non-zero, then the bilinear evaluation is also non-zero. That's a non-singular bilinear map. Now, if you take a non-singular bilinear map and you restrict it to the unit sphere in one coordinate and the unit ball in another coordinate, then, at each point in the sphere, this map is an embedding. It's a linear embedding by non-singularity. Thus, again, currying, uncurrying, whatever, gives you a ZMod2 map from SP minus 1 into the space of embeddings. Okay, so saying there is a non-singular bilinear map implies that there is such the coindex of this space is at least P minus 1. We don't know when non-singular bilinear maps exist, right? We cannot classify the triples P, Q, and D where these exist. Now, as a corollary of what we did, we get if the non-negative integers P and D minus P do not share any common ones in their binary expansion, then the coindex of this embedding space of a P plus 1 dimensional ball into RD is precisely D minus P minus 1. So let me try to, what have we done here? So a non-singular bilinear map is the same thing as, you can intuitively think about it as a linear family of linear embeddings, right? The first entry is a family, a linear family, and then the second entry gives you linear embeddings. And the corollary above gives a precise bound for skew family, meaning Z mod 2 equivariant family, that's less than being linear, of embeddings, that's less than linear embeddings. And these bounds generalize earlier non-existence results for non-singular bilinear maps. Yeah, so there's a series of paper by Lam and also this later paper, and all these non-existence results for non-singular bilinear maps are generalized by this. Oh, I could talk about this. Am I at 35 minutes? I should probably stop at this point.
Yeah, I think that'd be good.
Okay, I'll stop at this point. Thank you very much.
Thank you. And I suggest we unmute ourselves to thank Florian for the wonderful talk. Any other questions?
For this very last result, do you have to take the specific triangulation of D, say, coming from a simplex?
Yeah, so here you can just use the simplex as a triangulation. That's right. Mhm.
So if instead of bilinear forms, okay, sorry, just cancel my question, sorry.
So R, C, H, and I guess O give examples of these bilinear forms, and this is essentially the same as the previous setting, yes.
I'm not sure. What is
Yeah, I'm sorry. So the multiplication in R, C, H, and O give the example of such bilinear forms. Yes,
that's right. Right.
So
and this, you see this, right? You see this in these bounds, right? This 4 is quaternions, yes. This 8 is octonions. And you can't do better than that, right? These bounds, the lower bounds are not interesting here. What's interesting are the upper bounds. There are no more embeddings than what you get from saying, aha, RP2 embeds into, R16, and now you use quaternionic multiplication 4 times, and that's all you can do.
I see. Great. So this gives you sort of alternative proof, or
alternative proof of non-existence results for non-singular bilinear maps, for example. Yes.
I see.
Florian, did you start thinking about chirality or bilinear forms, or did one lead into the other, or did you have a general perspective that you expected to lead to both at once?
I mean, as usual in math, the history that I'm telling you is completely made up, right? This is not how I got to this question. No, so Mike is very interested, my co-author, Mike Harrison. He's very interested in non-singular bilinear maps and their various applications and implications in topology and differential geometry. So we started thinking about bilinear maps and whether we could extend certain notions about bilinear maps to other settings. And we then noticed that, so we first proved a very general result. And we only then noticed that it implies a chirality result that perhaps people find interesting already.
So just out of curiosity, are there any equivariant homology lurking around?
Yeah, equivariant cohomology is how one proves the non-existence of the maps. So I have 2 spheres, a product of 2 spheres, and I want to show that there is no Z mod 2 squared equivariant map into another sphere. And one way to prove this is to compute the so-called index in equivariant cohomology of these spaces, right? And that's where, I mean, the giveaway somehow is, why do I have this even? Do I have this up here somewhere? No, sorry. The giveaway, of course, is, where do I have this? Here, right? There are no common ones in their binary expansion. Well, you know, if you compute this thing in equivariant cohomology, then, and maybe in most cases, Hopf has already done this for you, only he didn't phrase it in this language, then, you know, you get binomial coefficients and they have to be 0. And that's where the no common ones in their binary expansion comes from. Sorry, they have to be non-zero.
Oh, I see. Thank you.
I can't tell you much about the chemistry, but I do want to say those chemistry papers, some of them are written for a general scientific audience or even general audience. They're quite interesting. So if you're interested in this type of stuff, I guess, you know, some chemistry papers might be interesting.
Okay, again, thank you for the talk, and